Welcome to a visual analysis of fire incidents in California. Here we will visualize the spatial distribution of fires in California, taking into account how they accumulate among different counties of the state. We will also look at what amount of damage have natural parks in the state received from these fire incidents. Lastly, we will examine if there is a relationship between the evolution in average precipitation per county and the count of fire incidents per county. Let's begin by importing the main dataset. This is a dataset from Kaggle describing fire incidents in California from 2013 to 2020. These are the most relevant fields. For one, we have the number of acres burned in the fire, the start date of the fire, as well as the position of the fire. In order to introduce this data to Carto, we followed the following steps. First, we filtered out outliers, both geographically and temporally speaking, with a SQL query. We added three widgets which add user interactivity to the visualization. Moreover, a visual encoding for the marker size was applied, basically linking marker size with the number of acres burned in each fire incident. In order to clarify this visual encoding, a legend was used. Lastly, a click pop-up was employed to show fire name, date, and extension in case the user wants more detail. This is the result of the simple import. Now, later on, we will analyze counties individually. Thus, it is necessary to import county boundary data. This has been obtained from the California Open Data Portal. So first, a new layer of polygons has been defined with the state's county boundaries. Later on, we will see how we fill these polygons according to a relevant variable, which we will import later on once again. Once we have the boundaries in Carto, we applied an intersect and aggregate analysis, which counts the number of fire incidents for each county. And lastly, another on-click pop-up was used to display county name and other relevant information for the user. This is the result of the simple import without taking into account visual encodings in the fill color of each polygon. Now, in order to introduce park data, since we want to analyze the effect of fire incidents on natural parks of California, two data sources have been employed: the California Department of Parks and Recreation and the National Park Services, one for state parks and another for national parks. Since this analysis focuses only on natural parks and not differentiating between state or national parks, although two layers have been defined for these two datasets, both layers have the same styling, making sure that the color used for these polygons is differentiable from county data, which, as we have mentioned, will be filled by a color later on. Moreover, a legend has been added in order to distinguish natural parks from the county encoding. This is a result of this import of natural park data. Lastly, precipitation data has to be added in order to encode the color filling each county polygon according to the evolution of annual precipitation per county. This data has been obtained by the National Oceanic and Atmospheric Administration, which has the following fields. For each county in California, the annual precipitation mean for the past century is included. Moreover, for the time span analyzed in the current study, that is from 2013 to 2020, the anomaly in average annual precipitation has been placed. This anomaly is measured with respect to the mean of the past century. Precisely this anomaly is the variable that will be used in order to color the inside of these county polygons. Before these can be introduced, simple formatting has been used. It has been learned and knowledge that Carto performs SQL join within behind the scenes, sorry, and thus it is necessary for the formatting of both tables to be similar. Thus, this join behind the scene is performed within add columns from second dataset analysis, which basically has been applied to the county's dataset. We just added precipitation data to an existing dataset of counties. Once this analysis has been carried out, a color bar or color scheme has been selected for the visual encoding of the fill color of each state, and a legend with a color bar employed has been defined to clarify the range of values employed in this color scheme. Lastly, a widget for the average county precipitation has also been included. This is the result of the color encoding according to the anomaly in average annual precipitation per county. Let's look at the map closer with Carto. Now, what we see here is precisely what has been described. We see this legend, which basically indicates how size of each marker is related with the acres burned by the fire. We can also see how natural parks are shown, since one has to distinguish these green polygons from the rest of the county polygons. And also the color bar showing the visual encoding of each county fill color is also shown. We can see how the precipitation anomaly is indicated and ranging from negative values to positive values. Moreover, with respect to the widgets, it is useful to include this start date widget precisely at the bottom of the screen, since it can have a very large width, and we can see the temporal evolution of fire incidents in California for the 2013 to 2020 range. Precisely, one can see that there has been, unfortunately, a peak or a growth in the number of fire incidents, although these frequently occur during the summer months. If we look a bit closer, we can see how the pop-ups we defined previously function. For each county, we can see how fire incidents, the precipitation anomaly, and the average precipitation in the past century are shown. Precipitation anomaly in this case is positive. That means it has rained more in these years, which are analyzed in this study, than on average on the past century. We can also click on each fire incident and see how data regarding this incident, acres burned, the name of the fire, and the start date. If we begin answering the questions posed for this study, one can see that the distribution of fire incidents is different in the north and in the southern part of the state. In the north and central part of the state, one can see two lines distributing for the distribution of fire incidents. These two lines are parallel to the coastline as well. There's a sort of gap in the middle of the state going down. Further south, these two lines converge in a single locus of fire incidents close to Los Angeles, San Bernardino, and San Diego. Now, if we look at the effect of fire incidents on natural parks, one can see that whereas the larger natural parks of the south of the state are not as affected, the smaller natural parks of the north of the state have had, most of the times, at least one fire incident. For instance, this natural park close to San Francisco has had a couple of fire incidents, whereas this other natural park closer to the north, sorry for that, has also been affected. Lastly, in order to examine whether there is a relationship between the evolution in annual precipitation and the amount of fire incidents, one can see that there is no such relationship. If we look at the northern counties of the state, one can see that precisely these counties close to Reno, Nevada, have a very large anomaly. That means in the past years it has rained more than in the past century. However, they still show up with a large amount of fire incidents. Precisely if we compare these counties to these counties in the middle between the coastline and Nevada, which have perhaps a smaller anomaly, but a smaller density of fire incidents. The same can be said for counties in the north closer to the coast. When we look at the south, the situation is a bit different, since we said that the fire incidents concentrated closer to Los Angeles. However, one can see for two states, these two counties, sorry, with a similar precipitation anomaly, one can see that the number of fire incidents in, let's say, San Bernardino is much smaller than the county of Los Angeles, although they both have a similar precipitation anomaly. Thus, for the southern part of the state, this makes one think of the distribution of population. One expects significantly high population densities close to Los Angeles, San Bernardino, and San Diego, whereas not as high population densities in the area between Los Angeles and Las Vegas, which is probably close to desertic. For the north of the state, this can be related with the distribution of vegetation. One would have to see how vegetation, the number of forests, is distributed along this northern part of the state, since it seems that perhaps if vegetation is the cause of this distribution, perhaps in the middle between both lines of fire incidents, there is not a dense, or there is, let's say, forests are not as frequent as in these two lines. In any case, I would say this analysis has been successful since we've gained more insights about how this unfortunate series of events have affected California and how they have distributed themselves along the state. Thank you.